Look up at the night sky tonight, and you'll see more than just stars. You'll see unanswered questions, cosmic riddles written in light across the darkness. What if I told you that every flicker of light out there holds a story we're only just learning to read? A story that rewrites the very fabric of reality as we know it. This isn't just about distant suns or swirling galaxies. It's about the revolutionary realms of existence itself, the hidden chapters of the universe waiting to be uncovered. And today, we're going to dive deep into those mysteries, peeling back layers of space and time to reveal truths that will leave you in awe. Think about the last time you felt truly small under that vast expanse of stars. That feeling isn't just wonder, it's a clue that there's so much more out there than we've ever imagined. From the explosive birth of galaxies to the invisible grip of dark matter, the cosmos operates by rules that defy our everyday logic. And here's the thing, every discovery we make only leads to more questions. What if time isn't what we think it is? What if the universe is hiding dimensions we can't even perceive? These aren't just science fiction ideas, they're the frontiers of real, cutting-edge research, and they're reshaping our understanding of everything. This journey isn't just for scientists or astronomers, it's for anyone who's ever looked up and felt that tug of curiosity. Because the universe isn't some distant, untouchable mystery. It's alive with secrets, and it's speaking to us in ways we're only beginning to understand. So if you've ever wondered what lies beyond the edge of our knowledge, if you've ever felt that thrill of the unknown, then you're already part of this story. Because today, we're not just observers, we're explorers, stepping into the revolutionary realms where the untold chapters of existence are waiting to be revealed. And trust me, by the end of this, you'll never see the night sky the same way again. Let's rewind time all the way back to the very beginning. Picture a moment so profound that it birthed not just stars or galaxies, but reality itself. The Big Bang wasn't an explosion in space. It was the explosion of space, a fiery dawn where time, matter, and energy burst into existence in a single, unimaginable instant. But how do we even know this happened? The answer lies in the faint afterglow still echoing across the cosmos. The cosmic microwave background radiation. It's like finding the universe's baby picture, a snapshot of that primordial heat frozen in time, barely warmer than absolute zero yet packed with clues. Scientists study these subtle ripples like detectives deciphering a cosmic fingerprint. Those tiny fluctuations in temperature, they're the seeds of everything, the blueprint for galaxies, stars, even us. Quantum fluctuations, smaller than atoms, were stretched across the newborn universe by inflation, a period of exponential expansion that lasted less than a blink but set the stage for all structure to form. Without those microscopic wrinkles in space-time, gravity would have had nothing to grip, and the universe might have remained a featureless sea of particles. But here's where it gets even wilder. What came before the Big Bang? Some theories suggest our universe is just one bubble in an endless multiverse, a froth of realities bubbling up from an eternal cosmic foam. Others propose a cyclical model where universes collapse and rebound in an infinite loop. And then there's the haunting possibility that time itself didn't exist before, that the question might be as meaningless as asking what's north of the North Pole. These primordial events didn't just shape the past, they dictated the future. As the universe cooled, particles clumped into atoms, then gas clouds, then the first stars, giant furnaces that forged the heavier elements in their cores. Every atom in your body was once stardust forged in those ancient explosions. So when you look up at the night sky, you're not just seeing distant lights. You're seeing the aftermath of creation, a story written in the very fabric of space, waiting to be read. Now imagine an architect who builds entire cities but leaves no fingerprints, no footprints, only the undeniable proof of their work. That's dark matter, the universe's invisible sculptor. We can't see it, touch it, or even detect it directly, yet without it, galaxies would fly apart, and the cosmos as we know it wouldn't exist. It's like gravity's silent partner, holding everything together while remaining utterly elusive. Scientists first stumbled onto this mystery in the 1930s, when astronomer Fritz Zwicky noticed something bizarre about galaxy clusters. They were moving too fast, so fast that their visible mass shouldn't have been enough to keep them from flinging apart. There had to be something else, something unseen, providing the extra gravitational glue. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars at the edges were orbiting just as fast as those near the center, defying the laws of motion unless some hidden mass was tugging on them. So what is dark matter? The leading candidates sound like something from a sci-fi novel. WIMP, weakly interacting massive particles, are hypothetical heavy particles that barely interact with normal matter except through gravity. Then there are actions, ultralight particles that could swarm through space like an invisible fog. Experiments deep underground, shielded from cosmic rays, hunt for the faintest whispers of these particles bumping into atomic nuclei. Meanwhile, the Large Hadron Collider smashes protons together at nearly the speed of light, hoping to create dark matter in the debris. But dark matter's influence isn't just theoretical. Look at the cosmic web, the vast scaffolding of the universe where galaxies cluster along filaments like dew on a spider's silk. Without dark matter's gravitational pull, this intricate structure would never have formed. Computer simulations show it clearly. When you include dark matter, virtual universes evolve just like ours. When you leave it out, they remain a formless haze. Yet for all its power, dark matter is only part of the story. There's something even more mysterious at work, a force that isn't holding the universe together, but tearing it apart. If dark matter is the universe's invisible glue, then dark energy is its shadowy push, a force so baffling it makes galaxies flee from one another at ever-increasing speeds. Picture this: you throw a ball into the air, expecting it to slow down and fall back. Instead, it rockets away faster and faster, defying gravity itself. That's exactly what's happening to our cosmos, and the discovery of this acceleration sent shockwaves through astronomy. The story begins in the late 1990s, when two teams of scientists were studying distant supernova exploding stars so bright they can outshine entire galaxies. These cosmic beacons act like mile markers, letting astronomers measure how fast the universe has expanded over billions of years. But the data revealed something impossible. The expansion wasn't slowing down as everyone expected. It was speeding up. It was as if the universe had slammed its foot on some unseen accelerator pedal. The only explanation, a mysterious repulsive force dubbed dark energy, making up a staggering 68% of the universe's total energy. What could it be? Einstein actually predicted something like this a century ago with his cosmological constant, a kind of built-in energy of empty space that counteracts gravity. He later called it his greatest blunder, but today it might be his greatest accidental triumph. Alternatively, dark energy could be a dynamic field, like an invisible fluid filling space, its strength waxing or waning over time. Some theories even suggest it's tied to extra dimensions or quantum fluctuations in the vacuum of space itself. The implications are staggering. If dark energy remains constant, the universe will expand forever, growing colder and emptier until galaxies vanish over the cosmic horizon. But if it grows stronger, space itself could tear apart in a catastrophic Big Rip, shredding atoms and spacetime in a final, violent act. Or perhaps dark energy will fade, allowing gravity to pull everything back together in a dramatic Big Crunch. And here's where black holes enter the stage, cosmic titans that might hold clues to this puzzle. Some theories suggest these gravitational monsters could eventually dominate the universe, swallowing matter and energy until they, too, evaporate into radiation over unimaginable eons. Others propose that black holes might somehow counteract dark energy, acting as cosmic anchors in the storm of expansion. One thing's certain: the dance between these two forces, dark energy's push and black holes' pull, will shape the ultimate fate of everything. Black holes aren't just cosmic vacuum cleaners, they're the universe's most extreme laboratories, where the rules of physics twist into paradoxes. Imagine a place so dense that not even light can escape its grip, where time slows to a crawl and space itself warps like rubber stretched to its limit. This isn't science fiction. Einstein's theory of general relativity predicted these monsters over a century ago, revealing that massive objects don't just pull on things, they bend the very fabric of spacetime. Yet for decades, black holes remained ghostly mathematical curiosities until science finally caught up with theory. The breakthrough came in April 2019, when the Event Horizon Telescope unveiled humanity's first glimpse of a black hole's shadow, a fiery ring of light circling the abyss of Messier 87, a supermassive beast 55 million light-years away. That glowing halo, it's the last desperate scream of matter spiraling toward oblivion, heated to billions of degrees before vanishing forever. But the real marvel was the darkness at the center, a perfect circle of nothingness, precisely the size Einstein's equations predicted. For the first time, we saw the universe's ultimate censorship at work, the event horizon, the point of no return where gravity wins its final battle against reality. Yet black holes aren't just cosmic dead ends. Stephen Hawking stunned the world when he revealed they could actually evaporate, leaking particles through quantum trickery at their edges. This Hawking radiation suggests that over eons, even these titans could fade away, but here's the catch. According to quantum mechanics, information can't be destroyed, yet black holes seem to erase it utterly. This paradox has physicists locked in a decades-long debate. Does information get scrambled and spit back out, or is it truly lost, rewriting the laws of physics in the process? And the mysteries only deepen near the edges. Take spaghettification, a gruesome yet fascinating fate for anything straying too close. The tidal forces near a black hole stretch objects into noodle-thin strands, atom by atom, as the difference in gravity between your head and feet becomes catastrophic. Meanwhile, at the center lies the singularity, a point of infinite density where all known physics breaks down. Some theories suggest it might be a gateway to other universes or dimensions, a wormhole disguised as annihilation. Others propose it's the birthplace of entirely new laws of nature, hidden from our view behind the event horizon's impenetrable veil. What happens inside remains one of science's greatest enigmas, but one thing's certain: black holes aren't just destroyers. They're cosmic alchemists, reshaping matter and energy in ways we're only beginning to fathom. And as we peer deeper into their shadows, we might just find the keys to unlocking the universe's deepest secrets. What if you could fold the universe like a piece of paper, punching a hole through the cosmic fabric to step from one side to the other in an instant? That's the promise of wormholes, hypothetical tunnels through spacetime that could act as cosmic shortcuts, linking distant corners of the universe or even different moments in time. Einstein's equations of general relativity suggest these bridges might exist, woven into the very geometry of reality. But here's the catch: the math allows them, yet nature seems to fight against their existence at every turn. Take the simplest model, known as an Einstein-Rosen bridge. Picture a black hole's singularity stretching into a narrow throat, emerging somewhere else as a white hole, a theoretical region where matter and light can only escape, never enter. The problem: these wormholes would snap shut faster than you could blink, crushed by their own gravity before anything could pass through. To keep one open, you'd need something truly bizarre: exotic matter with negative energy, a substance that repels rather than attracts. Think of it like trying to prop open a collapsing tunnel with anti-gravity pillars, something we've never observed in nature, though quantum physics hints that tiny amounts of negative energy might flicker in and out of existence at the smallest scales. Now imagine a stabilized wormhole, its throat held open just wide enough for a traveler. The possibilities ignite the imagination. A trip to the Andromeda Galaxy, 2.5 million light-years away, might take mere seconds instead of eons. Or consider time travel, because wormholes could connect not just places but different times. Stepping through one might send you into the past or future. But the universe has safeguards. Many physicists argue that any attempt to use a wormhole as a time machine would trigger a feedback loop of radiation, destroying the tunnel before paradoxes could unfold. It's as if reality itself has a built-in kill switch to prevent chaos. And then there's the quantum realm, where things get even stranger. Particles entangled at the quantum level appear to influence each other instantly across vast distances, as if connected by invisible threads. Some theories suggest this spooky action at a distance might involve microscopic wormholes, tiny bridges threading through an extra dimension we can't perceive. If true, the fabric of spacetime could be far more interconnected than we ever dreamed, with every particle subtly tied to every other through a hidden web of cosmic tunnels. So are wormholes just science fiction, or could they be lurking in the equations, waiting to be discovered? The answer might lie in the deepest laws of physics, where gravity and quantum mechanics finally shake hands. Until then, these cosmic shortcuts remain one of the universe's most tantalizing what-ifs, a reminder that reality, at its core, might be far stranger than even our boldest stories. Imagine two coins flipped on opposite sides of the universe, landing heads up in perfect unison every single time, not by chance, but because they're somehow bound by an invisible thread. That's quantum entanglement, one of the most baffling yet beautiful phenomena in physics. At its core, it's a connection so profound that changing the state of one particle instantly alters its partner, no matter how far apart they are. Einstein famously called it spooky action at a distance, because it defies everything classical physics taught us about how the universe should work. The magic lies in the math. When particles become entangled, they stop behaving as individual entities and start acting as a single quantum system. Measure one, and you instantly know the state of the other, even if it's light years away. This isn't just theoretical. In the 1980s, physicist Elaine Aspect conducted groundbreaking experiments using entangled photons, proving that this connection happens faster than light could travel between them. Later, the Bell test experiment slammed the door on any classical explanations, showing that entanglement isn't just real, it's a fundamental feature of reality. But how does it work? The unsettling truth is, we don't fully know. Some theories suggest that entangled particles might be tapping into hidden dimensions, communicating through shortcuts in spacetime we can't perceive. Others propose that the universe is fundamentally non-local, meaning objects can influence each other without any physical medium. It's as if the cosmos is woven together by an invisible web, with every particle subtly aware of its counterparts. This eerie interconnectedness has led some to wonder, could entanglement hint at a deeper unity in the universe, a hidden layer where separation is an illusion and everything is part of a grand cosmic whole? Philosophers and physicists alike have pondered whether this phenomenon might one day bridge the gap between quantum mechanics and gravity, or even reveal clues about consciousness itself. And here's where our story takes an even wilder turn. If entanglement truly links particles across vast distances, could advanced civilizations be using it to communicate? Scientists have already proposed quantum networks that leverage entanglement for unhackable encryption. So who's to say an alien civilization hasn't mastered this technology on an interstellar scale? The search for extraterrestrial intelligence might one day shift from scanning radio waves to detecting quantum signals, whispers of contact encoded in the very fabric of spacetime. The more we learn about entanglement, the clearer it becomes. The universe is far stranger and far more connected than we ever dared to imagine. And if spooky action really does tie everything together, then perhaps we're not just observers of the cosmos, we're participants in a dance older than time itself. For over 60 years, humanity has been leaning into the cosmic static, straining to hear a whisper that would change everything, proof that we're not alone. The search for extraterrestrial intelligence, or SETI, isn't just about antennas and algorithms. It's a profound act of hope, a collective ear pressed to the universe's door. Picture this: vast radio telescopes like the one at Arecibo, now immortalized in films and folklore, sweeping the sky for patterns amidst the noise. These aren't random scans. Scientists target sun-like stars and exoplanets in habitable zones, hunting for signals that stand out from nature's chaos, a deliberate pulse, a mathematical sequence, anything that screams artificial. But radio waves are just the beginning. Optical SETI scans for laser flashes, bursts of light that could carry encoded messages across the void. Imagine an alien civilization beaming a spotlight our way, a cosmic Morse code flickering between the stars. Yet silence persists, and that silence has a name: the Fermi paradox. If the universe is so vast, so ancient, why haven't we found a single trace of other civilizations? Enrico Fermi posed this haunting question over lunch in 1950, and it still echoes today. One answer is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. Maybe it's behind us, a rare fluke that let Earth slip through. Or worse, it's ahead, some catastrophic fate that dooms all advanced societies. Other theories suggest aliens might be too different to recognize, their technology or biology beyond our comprehension. Or perhaps they're deliberately hiding, watching us like specimens in a galactic zoo. But what if we do make contact? The societal shockwaves would ripple through every aspect of human life. Religions might reinterpret their teachings, governments would scramble to draft interstellar policies, and philosophers would wrestle with humanity's place in a crowded cosmos. The discovery could unify us as a species or fracture us further. History shows how cultures react when worldviews collide. The arrival of an alien, other, would dwarf all previous encounters. Closer to home, our own solar system holds its own enigmas. Europa's hidden ocean, Saturn's methane lakes, even Mars' fleeting methane spikes, each is a tantalizing hint that life, if not intelligence, might be lurking next door. The line between science fiction and science fact blurs when we consider that the first aliens we meet might not be radio engineers but microbes in icy plumes. A humbling reminder that life could be both everywhere and unrecognizable. The search continues, not just with telescopes but with rovers, submarines, and landers, peeling back the layers of our cosmic backyard. And with every unanswered signal, every unexplored moon, the universe whispers back, keep looking. Mars has always been the planet of contradictions, a rust-colored world with valleys carved by ancient rivers, yet now so dry that its soil is more inhospitable than Earth's driest deserts. Look at those winding channels and dried-up lake beds, and it's impossible not to wonder, what happened here? Billions of years ago, Mars may have been a twin to early Earth with thick skies, flowing water, and maybe even life. Today, it's a frozen desert, but beneath that barren surface, secrets are waiting. Take the Curiosity rover's discoveries in Gale Crater, an ancient lake bed the size of Connecticut. Buried in the rocks, it found organic molecules, carbon-based compounds that are the building blocks of life. Not proof of life itself, but a tantalizing clue that the ingredients were there. Then there's the methane. On Earth, most methane comes from living things, and on Mars, it appears in mysterious seasonal spikes. Could it be seeping from underground microbes, or is it just the result of geological processes we don't fully understand? The Perseverance rover is now collecting samples that might hold the answer, sealing them in tubes for a future mission to bring back to Earth. But here's the twist. If life ever existed on Mars, it might not be extinct. Deep below the surface, shielded from radiation, there could be reservoirs of liquid water kept warm by geothermal heat. On Earth, we've found microbes thriving miles underground in similar conditions. Why not Mars? Some scientists even speculate about a shadow biosphere, organisms so alien that they don't resemble any life we know, hiding in cracks and caves we've yet to explore. And while Mars captivates us with its maybes, the outer solar system holds even stranger possibilities. Fly past the red planet, and you'll reach Jupiter's moon Europa, a frozen world with an ocean hidden beneath its icy crust. Twice as much water as Earth's oceans, all trapped under miles of ice, but where there's water, there could be life. Then there's Saturn's moon Enceladus, spewing geysers of water vapor into space, with organic molecules dancing in the spray. These aren't just dead rocks, they're dynamic worlds whispering the same tantalizing question. If life could start here in these dark, distant oceans, then where else might it be hiding? The search isn't just about finding aliens, it's about understanding how life begins, how rare or common it might be, and what that means for our place in the cosmos. Every rover digging in the dust, every probe diving through icy plumes, is rewriting the story of life itself. And with each discovery, the universe feels a little less lonely, a little more alive with possibility. Beneath the icy crusts of Europa and Enceladus, entire oceans churn in perpetual darkness, vast, liquid worlds hidden from the sun's reach, yet possibly teeming with life. These aren't the frozen wastelands they appear to be. Europa, Jupiter's enigmatic moon, harbors an ocean so deep it could hold twice the water of Earth's seas, all trapped under miles of ice. And Enceladus, Saturn's tiny, gleaming satellite, sprays its secrets into space through towering geysers, offering free samples of its subsurface ocean to anyone clever enough to catch them. The implications are staggering. If life can thrive in these sunless depths, then the universe might be far more hospitable than we ever imagined. The key lies in hydrothermal vents, cracks in the ocean floor where superheated water, rich in minerals, gushes into the icy darkness. On Earth, these vents are oases of life, hosting bizarre creatures like tube worms and extremophile bacteria that thrive on chemicals rather than sunlight. If similar vents exist on Europa or Enceladus, they could provide the energy and nutrients needed for alien ecosystems to flourish. Imagine microbes adapted to crushing pressures and freezing temperatures, their biochemistry utterly foreign to ours, yet alive in ways we're only beginning to comprehend. NASA Europa Clipper mission, launching in the next few years, aims to answer these questions. Orbiting Jupiter, it will fly past Europa dozens of times, using ice-penetrating radar to map the hidden ocean and spectrometers to analyze plumes erupting from the surface. Even more tantalizing, the possibility of a future lander equipped to drill through the ice, sending a submersible into the abyss, a robotic explorer diving into an alien sea. Meanwhile, proposals for Enceladus missions dream of flying through its geysers, capturing droplets of ocean water to search for organic molecules or even cellular structures. But why stop at our solar system? The discovery of exoplanets' worlds orbiting distant stars has exploded in recent years, with thousands confirmed and billions likely waiting. Among them are ocean worlds similar to Europa, planets entirely shrouded in ice with liquid layers beneath. Some, like those in the TRAPPIST-1 system, orbit in the habitable zone where temperatures might allow surface oceans. Others, like Proxima Centauri b, could have subsurface seas despite being bathed in harsh radiation. The more we learn about Europa and Enceladus, the better we can interpret the whispers of data from these distant cousins. The hunt for life beyond Earth isn't just about finding aliens, it's about redefining what life is. Extremophiles on Earth have already shattered our assumptions, thriving in acid, boiling water, even the vacuum of space. If organisms can survive there, why not in the icy depths of Europa or the saltwater plumes of Enceladus? Each mission, each discovery, pulls us closer to answering humanity's oldest question: are we alone? And with every clue, the universe seems to whisper back, look deeper. Beyond our solar system, tucked into the glow of distant stars, lie worlds stranger than anything we've dreamed, planets where molten iron rains from the sky, where diamond mountains gleam under twin suns, where years pass in a matter of days. These are exoplanets, and their discovery has rewritten the cosmic rulebook. Take hot Jupiters, for example, gas giants so close to their stars that their atmospheres are literally boiling away, leaving comet-like tails of vaporized metal. Or the diamond planet 55 Cancri, a super-Earth where scientists believe a third of its mass could be crystallized carbon, crushed into gemstone by unimaginable pressures. Detecting these alien worlds is a feat of cosmic detective work. The Transiting Exoplanet Survey Satellite, or TESS, scans 200,000 stars for the telltale dip in brightness when a planet crosses their face, like spotting a moth fluttering past a street lamp from miles away. But the James Webb Space Telescope takes it further, dissecting the light filtered through exoplanet atmospheres, hunting for chemical fingerprints like methane or water vapor. Imagine analyzing the colors of a sunset on a world 60 light-years distant, searching for hints of life in the faintest glow. The real prize, though, lies in the habitable zone, the Goldilocks region where liquid water could pool on a planet's surface. Kepler 452b, nicknamed Earth's cousin, orbits its star at just the right distance, basking in similar warmth. Then there's the 7 rocky planets of TRAPPIST-1, huddled so close that standing on one would reveal neighboring worlds hanging in the sky like glowing marbles. But habitability isn't just about location. Tidally locked planets with one side eternally scorched and the other frozen might harbor life in the twilight ribbon between. And then there are the anomalies, the cosmic head-scratchers, like Kelt 9b, a planet hotter than most stars, where molecules tear apart in the 2,700 degrees Celsius heat. Or the rogue planets untethered from any star, drifting through the void with only their internal heat to sustain potential life, most baffling of all. Tabby's star, whose erratic dimming sparked theories of alien megastructures before dust clouds, offered a more mundane, but still unsolved explanation. Each discovery peels back another layer of possibility. proving that the universe doesn't just host other worlds, it specializes in the extraordinary. And as our telescopes grow sharper, we're not just mapping planets, we're stepping into a gallery of cosmic wonders where every new find challenges what we thought was possible. One moment, the cosmos is silent. The next, a blast of radio waves brighter than 1 billion suns tears through the darkness, then vanishes without a trace. Fast radio bursts are one of space's most electrifying puzzles. Flashes of energy so powerful they outshine entire galaxies for a fraction of a second. First detected in 2007, these bursts travel billions of light years only to disappear before we can pinpoint their origins. It's like hearing a gunshot in the dark, but when you turn on the lights, there's no shooter, just the echo of something unimaginable. The leading suspect, magnetars neutron stars with magnetic fields so intense they could strip the atoms from your body at 1,000 kilometers away. When these cosmic powerhouses quake or snap, they might unleash bursts of energy detectable across the universe. In 2020, astronomers caught one red-handed. A magnetar in our own galaxy fired off a burst eerily similar to those from deep space. But here's the twist: not all fast radio bursts fit this pattern. Some repeat at irregular intervals, others flare just once and never return. If magnetars explain some, what's behind the rest? Then there's the tantalizing fringe theory: could these bursts be artificial? Some scientists have floated the idea of alien megastructures, like colossal transmitters powering interstellar beacons or even light sails for spacecraft. While unlikely, the possibility forces us to ask, how would we recognize an intentional signal amid nature's chaos? The truth is, we might already be hearing alien technology and mistaking it for stellar fireworks. But fast radio bursts aren't just cosmic curiosities, they're tools. As these waves streak across the universe, they pass through clouds of ionized gas that slow and scatter their frequencies. By measuring this distortion, astronomers can map the invisible matter between galaxies, the so-called missing baryons that theories say should exist but telescopes can't see. It's like using lightning to illuminate a foggy landscape. Each burst reveals the hidden contours of the cosmos. And just when you think space can't get stranger, consider the rogue planets, worlds untethered from any star, drifting through the void like cosmic nomads. Some may have been flung from their birth systems by gravitational chaos. Others might have formed alone in the dark, without a sun to warm them. They're frozen wastelands, yet beneath icy crusts, tidal forces or radioactive decay could sustain subsurface oceans. Imagine life evolving around hydrothermal vents on a planet wandering forever between the stars, its entire history written in darkness. The universe never runs out of ways to surprise us. Picture a world with no sunrise, no sunset, just endless night stretching in every direction. Rogue planets are the cosmic nomads of the universe, untethered from any star, drifting through the void like ghost ships in the interstellar dark. Some were flung from their birth systems by violent gravitational encounters. Others may have formed alone in the cold embrace of space. Without a sun to warm them, their surfaces plunged to temperatures near absolute zero, their atmospheres frozen solid. Yet beneath that icy crust, something astonishing might be hiding. Vast subsurface oceans kept liquid by the slow churn of radioactive decay or the gravitational squeezing of a nearby moon. Finding these invisible wanderers is like spotting a needle in a galaxy-sized haystack. Astronomers use a trick called gravitational microlensing, where a rogue planet's gravity bends and brightens the light of a distant star as it passes in front, revealing its presence like a cosmic magnifying glass. Already, surveys like the optical gravitational lensing experiment have uncovered dozens of these free-floating worlds, some as small as Earth, others rivaling Jupiter. The numbers are staggering. For every star in the Milky Way, there could be 20 rogue planets adrift in the darkness, outnumbering their star-bound siblings by an unimaginable margin. But here's where it gets even wilder. If life exists on these frozen outcasts, it would defy everything we know about survival. Imagine extremophile microbes clustered around hydrothermal vents in pitch-black oceans, their entire ecosystem powered by chemistry rather than sunlight, like the creatures in Earth's deepest trenches, but isolated for billions of years. Some scientists speculate that rogue planets could be galactic arcs, carrying life between star systems as they wander. If true, life might not need a star at all, just liquid water and a source of heat, no matter how faint. This brings us to a deeper mystery, the cosmic fine-tuning problem. Why does our universe seem perfectly calibrated for life? The gravitational constant, the strength of electromagnetism, even the density of dark energy. If any of these were slightly different, stars wouldn't form, atoms wouldn't bond, and life as we know it would be impossible. Some call it luck, others see the fingerprints of a multiverse where countless universes with random laws exist, and we simply inhabit the one where everything lined up just right. Rogue planets amplify this enigma. If life can thrive in the most hostile corners of the cosmos on worlds without light, without warmth, without stars, then the universe might be far more generous than we ever dared to dream. The rules we thought were absolute might just be suggestions, and the story of life could be unfolding in ways we're only beginning to imagine. The numbers don't add up, not unless the universe wanted us here. Consider the gravitational constant, the precise strength that holds stars together and keeps planets in orbit. If it were slightly weaker, matter would never clump into galaxies. Stronger, and the universe would have collapsed back on itself eons ago. Or take the cosmological constant, the energy density of empty space. Tweak it by 1 part in 120 digits, and either everything would fly apart too fast for atoms to form, or gravity would crush all structure before it could begin. This isn't just luck, it's like winning the lottery 1 trillion times in a row. So how do we explain this razor's edge precision? The anthropic principle offers one answer. We're here to observe these constants because they allow our existence. In an infinite variety of universes with random laws, we'd naturally find ourselves in the one where conditions are just right. It's the cosmic equivalent of a puddle marveling at how perfectly its hole fits it. But the multiverse theory takes this further, suggesting our universe is just one bubble in an endless froth of realities, each with different physical rules. Most might be barren, lifeless voids, but we're in the rare one where the dials landed on life. Yet some see a deeper pattern here. The constants align with mathematical elegance, as if solving an equation we haven't fully grasped. Could there be an undiscovered law that locks these values into place? Or does this fine-tuning hint at something more profound, a universe not just allowing life but expecting it? Philosophers and physicists alike have wrestled with this question for decades, with answers ranging from pure chance to the tantalizing possibility of a cosmic architect. Now shift your perspective entirely. What if the universe's fine-tuning isn't about laws written in stone, but about information encoded on a surface we can't see? This is the holographic principle, the radical idea that all the complexity of our three-dimensional reality might be projected from a two-dimensional boundary at the edge of space, like a movie playing on the walls of the cosmos. If true, the constants we measure could be shadows of deeper code, pixels in a vast cosmic display. Suddenly, the fine-tuning problem isn't just about why these numbers, but what's rendering them, and the answers might rewrite everything we know about existence itself. What if everything you see, the stars, your hands, even the screen in front of you, is just an elaborate illusion, a three-dimensional movie projected from a two-dimensional surface at the edge of the cosmos. This isn't science fiction, it's the holographic principle, one of the most mind-bending ideas in modern physics. The theory emerged from a startling discovery about black holes. When matter falls into one, it vanishes from our universe, but according to quantum mechanics, information can't be destroyed. So where does it go? Stephen Hawking and others realized the data might be encoded on the black hole's event horizon, the point of no return, like a cosmic hard drive storing everything that ever crossed its threshold. If a black hole's surface can hold information about its contents, could the entire universe work the same way? String theory takes this further, suggesting that the three-dimensional world we experience might be a projection from a vast, flat boundary we can't perceive, like watching a movie where the screen is hidden behind the scenes. The math checks out. The equations describing events in our universe can be rewritten as interactions happening on this distant two-dimensional surface. It's as if reality is a hologram with depth and texture emerging from patterns etched on some unimaginable cosmic canvas. Even more bizarre, this could explain why the universe appears fine-tuned for life. If the constants of nature aren't fundamental but instead pixels in a grand simulation, their precise values might be adjustable settings in a deeper code. But how do we test something this radical? Enter the holometer experiment at Fermilab, a device designed to hunt for quantum fuzz, tiny fluctuations in spacetime that would betray its pixelated nature. Think of it like holding your hand up to a projector. If reality is a hologram, there should be a limit to how finely detailed it can be, a subtle graininess at the smallest scales. So far, the results are inconclusive, but the hunt continues. Meanwhile, researchers are studying the cosmic microwave background for anomalies, searching for imprints of a universe encoded on a hidden surface. And here's where time enters the equation. If space is an illusion, what does that mean for time? In holographic theory, time might not flow the way we experience it. Instead, it could emerge from the way information is processed on that distant boundary, like the ticking of a cosmic clock we're all trapped inside. This reshapes even black holes. Their infamous singularities might not be points of infinite density but glitches in the projection, places where the code breaks down. The implications are staggering. If the holographic principle is true, then free will, consciousness, even the passage of time could all be side effects of a deeper reality we're only beginning to glimpse. It's a reminder that the universe doesn't just hold mysteries, it might be a puzzle wrapped in layers we're only now learning to peel back. Time might feel like the most solid thing we know, the steady tick of a clock, the unshakable march from past to future. But peel back the layers, and you start to see the cracks in that illusion. Einstein shattered our common-sense view over a century ago when he revealed that time isn't some universal metronome, it's fluid, stretchable, even bendable. Near a black hole where gravity twists space-time like taffy, time slows to a crawl. An astronaut falling toward the event horizon would appear to freeze in place from your perspective, their final moments stretched across eternity. Yet for them, time would pass normally, proof that the now you're experiencing is entirely relative. This leads us to eternalism, the radical idea that past, present, and future all exist simultaneously in a static, block universe. Think of reality as a loaf of sliced bread. Every moment, your birth, the dinosaur's reign, the heat-death of the cosmos already exists like a fixed slice in the loaf. Your sense of time flowing is just an illusion, a trick of consciousness moving through these frozen instants. It's a view supported by relativity, where events can't be objectively ordered. What's now, for you might be the past or future for someone moving at a different speed. But if time is an illusion, what creates our vivid sense of its passage? Some physicists point to entropy, the universe's tendency toward disorder. The reason we remember the past but not the future, they argue, is simply because entropy was lower back then, a cosmic arrow etched in the aftermath of the Big Bang. Others suggest time emerges from quantum entanglement, with the universe's interconnectedness creating a sort of clock that ticks as particles interact. Now take this one step further into the multiverse. If every quantum possibility spawns a new universe, as some interpretations suggest, then time might branch endlessly like a fractal tree. Your choices wouldn't just shape your future, they'd spin off alternate versions of reality where every possible outcome plays out. Suddenly, the linear timeline we cling to seems like a tiny thread in an infinite tapestry of parallel nows. So is time real or just a useful fiction? The answer might lie in black holes once more, at the singularity where space-time curvature becomes infinite. Time as we know it ceases to exist. Equations break down, leaving physicists to wonder, is this where the illusion shatters, revealing time as nothing more than a convenient tool, a way for the universe to keep events from happening all at once? Until we solve that riddle, time remains both our most familiar companion and the cosmos' greatest sleight of hand. What if every choice you've ever made, every path taken or not taken, exists simultaneously in an endless tapestry of alternate realities? The idea of parallel universes isn't just science fiction. It's a serious scientific hypothesis with roots in the bizarre world of quantum mechanics. Take the many worlds interpretation. Every time a quantum particle faces multiple possible states, the universe doesn't just pick one, it branches, spawning new realities where each outcome plays out. That coffee cup you knocked over this morning, in one universe it never toppled, in another it shattered into 1,000 pieces, and in some distant corner of the multiverse, you might even be sipping from it right now, reading these words in an entirely different context. But quantum branching isn't the only path to parallel worlds. Inflationary cosmology paints an even grander picture. During the universe's explosive infancy, space expanded faster than light, creating vast, isolated bubbles of reality, each with its own unique physics. Some might have stronger gravity, others with no dark energy at all. A handful could even harbor life forms unimaginable to us, thriving under laws of nature we'd find utterly alien. The math suggests these bubbles could be infinite in number, floating in an unfathomably vast megaverse like soap suds in a cosmic sink. Now for the million-dollar question, could we ever detect these other realms? The odds seem slim. These universes likely exist beyond our cosmic horizon, forever separated by stretches of inflating space we can't cross. But some theorists propose subtle clues might linger in the cosmic microwave background, like faint bruises from collisions with neighboring bubble universes in the early cosmos. Others speculate that quantum entanglement could be a ghostly handshake between realities, particles whispering to their counterparts across the multiverse. This leads us to an even more profound mystery, the role of consciousness in shaping reality. Quantum experiments show that particles exist in superposition, multiple states at once, until observed. Does the act of observation collapse these possibilities into one reality, or does the observer's awareness itself split into parallel streams? Some interpretations suggest consciousness isn't just a passive witness, but an active participant in the fabric of existence, weaving reality from an infinite loom of possibilities. So where does that leave us, staring into the void between stars, wondering if somewhere out there, another version of you is staring back, not as a mirror image, but as a living testament to the universe's boundless creativity? The multiverse isn't just a theory, It's an invitation to reimagine our place in the cosmos, where every possibility, no matter how improbable, finds its home. And that changes everything. What if the universe isn't just aware of us? What if it's aware through us? The idea that consciousness might be woven into the fabric of reality isn't just philosophy. It's a hypothesis with roots in the strangest corners of quantum physics. Take the observer effect. In the famous double-slit experiment, particles behave as waves when no one's watching, collapsing into definite positions only when measured. It's as if reality waits for an audience before deciding what to be. This isn't just about human observation. It suggests that awareness itself might play a role in shaping existence, blurring the line between the observer and the observed. Enter panpsychism, the radical view that consciousness isn't a product of complex brains but a fundamental property of matter, like mass or charge. In this framework, even electrons might possess a whisper of experience, a primitive form of feeling. The universe wouldn't have developed consciousness. It would have started with it, building up from these tiny sparks into the rich self-awareness we know. Think of it like temperature. Individual atoms don't have heat, but collectively they create it. Could consciousness emerge the same way, with the cosmos itself as the ultimate mind? Some scientists push further, suggesting the universe might not just contain consciousness, it might be conscious. Integrated information theory, for instance, proposes that any system with enough interconnected complexity could experience subjectivity. If that's true, then the cosmic web of galaxies, with its vast networks of gravitational and quantum connections, might qualify as a kind of cosmic brain. Even black holes, those voracious devourers of information, could be nodes in this grand neural network, processing reality in ways we can't fathom. But how do we test such mind-bending ideas? Laboratories are already probing the boundaries of consciousness and quantum mechanics. Experiments with human subjects observing quantum systems aim to see if intention can influence outcomes at the subatomic level. Meanwhile, telescopes scan the cosmos for large-scale patterns that might hint at a universe thinking in slow geological time. The line between metaphysics and physics grows thinner by the day. This brings us to the next frontier, the future of cosmic exploration. If consciousness is fundamental, then our quest to understand the universe becomes a kind of cosmic self-discovery. Every probe we launch, every telescope we build, isn't just exploring outer space, it's peering into the deeper layers of a reality that might be more alive, more interconnected than we ever dared to dream. And that changes not just how we see the stars, but how we see ourselves. Imagine a spacecraft gliding between the stars, not in centuries, but in mere decades. A vessel carrying the first human footsteps into the interstellar void. This isn't just science fiction, it's a dream humanity is inching toward with every breakthrough. The challenges are staggering. The nearest star, Proxima Centauri, lies 4.2 light-years away. With today's fastest rockets, that journey would take 75,000 years. But what if we could bend the rules of physics, or at least push them to their limits? Take generation ships, colossal arcs where multiple generations of astronauts would live and die before reaching their destination. These floating civilizations would need self-sustaining ecosystems, artificial gravity, and shielding against cosmic radiation, technologies we're only beginning to explore. The psychological toll would be immense. Imagine spending your entire life in a metal hull, knowing your grandchildren might be the first to see sunlight from another star. Yet for some, the appeal is irresistible. Projects like the Daedalus interstellar probe, designed in the 1970s, proved that fusion-powered ships could theoretically reach 12% of light speed, cutting the travel time to a mere 50 years. Then there's the allure of antimatter, the universe's most potent fuel. When matter and antimatter collide, they annihilate in a burst of pure energy efficiency, unmatched by any chemical or nuclear reaction. Just 1 gram could power a city for a day. The catch: antimatter is fiendishly hard to produce and store. CERN creates infinitesimal amounts at costs that would bankrupt nations, and containing it requires magnetic traps colder than deep space. But visionaries like physicist Robert Forward proposed antimatter-driven sails, where pellets of the stuff would detonate behind a spacecraft, propelling it forward like a nuclear pulse engine. For those seeking gentler solutions, laser sails offer a tantalizing alternative. Picture a wafer-thin craft, no heavier than a paperclip, unfurling a reflective sail miles wide. Ground-based lasers would bathe it in light, pushing it to relativistic speeds without onboard fuel. The Breakthrough Starshot initiative aims to do just that, sending thousands of microprobes to Alpha Centauri within 20 years. But even here, hurdles loom, maintaining laser precision over light years, shielding the sail from interstellar dust, and ensuring signals from probes 1 trillion miles away don't dissolve into the cosmic static. And what of the ethics? If we spread life beyond Earth, do we become stewards or invaders? Some argue that seeding microbes on habitable exoplanets could jumpstart evolution elsewhere, a cosmic gift. Others warn of unintended consequences, like disrupting alien ecosystems or triggering galactic-scale contamination. The debate echoes terrestrial dilemmas. Did explorers discover new lands or impose themselves where they didn't belong? The answer might shape not just our destiny, but the moral legacy of our species. This quest for the stars forces us to confront deeper questions about the fabric of reality itself. To travel between suns, we'll need more than advanced engines. We'll need a unified theory of physics, one that reconciles gravity with quantum mechanics. Perhaps the secret lies in manipulating spacetime itself, warping it like a folded sheet to bridge unimaginable distances. Until then, the stars remain both a challenge and a beacon, calling us to push beyond the limits of what we once thought possible. Physics has 2 towering pillars: quantum mechanics, ruling the subatomic world with probabilities and particles, and general relativity, painting gravity as the curvature of spacetime on cosmic scales. Both work flawlessly in their own domains, yet when they collide, the math explodes into nonsense. Black holes and the Big Bang become riddles we can't solve without a deeper language, a single set of rules that stitches these theories together. This is the theory of everything, the most elusive prize in science. String theory offers one dazzling possibility: that the universe's fundamental building blocks aren't particles but tiny, vibrating strings. Their different harmonies would create every force and particle we know, like cosmic notes played on invisible filaments. The math suggests these strings dance in 10 or 11 dimensions, with the extra ones curled up too small for us to perceive. Imagine ants crawling on a telephone wire. From their perspective, the wire seems one-dimensional, but in reality, it's a cylinder with hidden depth. String theory's elegance is undeniable, but critics argue it's untestable, a beautiful idea trapped in a maze of equations without experimental proof. Then there's loop quantum gravity, which reimagines spacetime itself as a fabric woven from finite, interlocking loops. Picture the universe as a mesh of tiny threads, where even time is granular, ticking forward in discrete steps like frames in a film. Unlike string theory's extra dimensions, this approach keeps spacetime four-dimensional but quantizes it, preventing the infinities that break relativity at singularities. The trade-off: it struggles to explain how smooth spacetime emerges from this pixelated web at large scales. A wild-card contender is Eric Verland's emergent gravity. proposing that gravity isn't a fundamental force but a side effect of entropy, the universe's tendency toward disorder. Think of it like the way crowd behavior emerges from individual choices. Gravity might arise from the way information is structured on the cosmic horizon. It's a radical departure from Einstein, but it neatly explains dark matter's effects without invoking invisible particles. Why does this search matter? Unifying physics wouldn't just satisfy intellectual curiosity, it could unlock technologies beyond our imagination. Mastery of quantum gravity might lead to warp drives, artificial black holes, or even control over spacetime itself. But the implications run deeper than engineering. A theory of everything could reveal whether our universe is inevitable or accidental, finely tuned or one of countless variations. Now, imagine pairing this quest with another revolution, artificial intelligence. AI already crunches data faster than any human team, spotting patterns in particle collisions or galaxy distributions that we'd miss. Future systems might devise entirely new physical theories, testing them in virtual universes before we even build the experiments. Some physicists speculate that AI could stumble upon the theory of everything not through raw intuition, but by finding hidden connections in the noise of centuries of research. Yet here's the haunting question: if the universe's deepest laws are beyond human comprehension, could AI become the first entity to truly understand them? And what would that mean for our place in the cosmos? The search for unification isn't just about equations. It's about discovering whether reality's ultimate nature is knowable, and who or what gets to know it. Artificial intelligence isn't just changing how we explore the cosmos, it's rewriting the rules of discovery itself. Picture a supercomputer sifting through decades of telescope images in seconds, spotting patterns invisible to human eyes. Already, machine learning has uncovered dozens of new gravitational lenses, cosmic magnifying glasses that bend light around massive galaxies by analyzing data from the Hubble Space Telescope. These algorithms don't get tired, don't overlook details, and never need coffee breaks. They're the perfect partners for astronomers drowning in petabytes of data from observatories like the James Webb Space Telescope, where every snapshot contains thousands of galaxies waiting to be catalogued and understood. But AI's role goes far beyond crunching numbers. At CERN Large Hadron Collider, neural networks reconstruct particle collisions so complex they'd take physicists months to decode manually. These systems don't just follow instructions, they learn, adapting their approaches to tease out subtle signals from the subatomic noise. Some even suggest the next revolutionary particle might be discovered not by a human staring at screens, but by an AI noticing an anomaly no one programmed it to find. This raises a profound question. Could artificial intelligence eventually grasp truths about reality that elude human minds? Consider string theory's 11 dimensions or the quantum nature of spacetime concepts that twist our brains into knots. An advanced AI free from biological constraints might navigate these conceptual labyrinths with ease, developing new physics frameworks we can barely comprehend. Philosopher Nick Bostrom speculates about post-intelligent machines that don't just solve problems but reframe them entirely, viewing the universe through perceptual lenses we lack. Yet with this potential comes existential unease. If AI unlocks the theory of everything, will it be able to explain it in terms we can understand? Or will we become like ants trying to grasp general relativity, forever limited by our cognitive architecture? Some theorists propose hybrid approaches where AI acts as a translator between cosmic truths and human comprehension, a kind of quantum Rosetta Stone bridging the knowable and the unimaginable. These possibilities ripple into philosophy's deepest waters. If consciousness shapes reality at quantum scales, as some interpretations suggest, could an artificial mind collapse the wave function differently than a biological one? Would its observations create alternate branches of reality? And if the universe is fundamentally mathematical, as Pythagoras and Einstein believed, might AI, pure math made sentient, become its ideal interpreter? We're not just building tools to explore the cosmos. We're creating potential successors in the grand quest for understanding, raising the dizzying possibility that the universe designed humans as stepping stones to intelligences better suited to decode its mysteries. The collision of artificial intelligence and cosmic exploration isn't just changing how we see the stars. It's forcing us to redefine what it means to discover, to understand, and ultimately, to be conscious in a universe that might contain minds beyond our wildest imaginings. Why is there something rather than nothing? This question cuts deeper than black holes or quantum mysteries. It strikes at the heart of existence itself. Every galaxy, every atom, every fleeting thought arises from a reality that, by all logic, didn't have to be. Theologians have wrestled with this for millennia, framing the universe as a deliberate act of creation, a divine breath exhaling being into the void. Yet science offers its own origin story, a quantum fluctuation in an unfathomable nothingness, a random burp in the fabric of emptiness that spawned everything. But randomness doesn't satisfy the hunger for why. If the universe popped into existence from nothing, what or who defined the rules that allowed it to happen? Philosophers like Leibniz argued that nothingness is simpler, more natural than existence. So why does the cosmos stubbornly persist? Some modern physicists propose a multiverse, where universes bubble up endlessly, each with different laws. We just happen to live in one where the numbers lined up for stars, planets, and life. It's the ultimate lottery, trillions of dead universes for every one that sparks consciousness. Others, like cosmologist Lawrence Krauss, suggest nothing isn't truly empty. It's a seething quantum foam where particles flicker in and out of existence. In that light, the universe isn't a miracle, it's an inevitable fluctuation, but even these theories dance around the deeper unease. Why does the quantum foam exist? Why do mathematical laws hold sway? Theologians might call this God, while scientists chase equations. Yet both paths converge on the same ore. The universe isn't just there, it's ordered, finely tuned for complexity. Whether by design or accident, that tuning demands explanation. Perhaps the answer lies beyond human categories. Eastern traditions like Buddhism frame existence as an endless cycle of arising and dissolving, where questions of why dissolve into direct experience. Meanwhile, existentialists like Sartre shrug. The universe is absurd and meaning is ours to create. Between these poles, one truth emerges. The question itself is our legacy. For billions of years, the cosmos expanded in silence. Then life awoke and started asking. This is the gift and the burden of consciousness, to stare into the abyss and insist it answers back. Every telescope pointed at the stars, every particle collider smashing atoms, every child gazing at the night sky. They are all chapters in humanity's love letter to the unknown. The universe may never explain itself, but in the asking, we become more than stardust. We become the universe thinking aloud. From the moment our ancestors first traced constellations in the night sky, something extraordinary awakened in us, a restlessness, a refusal to accept the horizon as the limit. This isn't just curiosity, it's coded into our DNA. 500 years ago, explorers like Magellan risked everything to sail off the edge of known maps. Today, we aim for the stars, but the drive is the same, to see what lies beyond, no matter the cost. Think of the Apollo astronauts standing on the moon's desolate surface, gazing back at Earth, a pale blue dot suspended in blackness. They didn't just bring back rocks, they brought back perspective, proof that humanity could reach beyond its cradle. What fuels this relentless expansion? It's more than practicality or survival. The same impulse that sent Polynesian voyagers across uncharted oceans now propels rovers across Martian dunes. We launched telescopes like Hubble and Webb not just to collect data, but to answer questions that have haunted us since the first campfire stories. Are we alone? How did all this begin? What's our place in the grand scheme? These aren't academic exercises, they're the echoes of a species that refuses to accept ignorance as permanent. Consider the audacity of modern astrophysics. We can't touch a black hole, yet we've mapped its shadow. We've never set foot on an exoplanet, but we've tasted its atmosphere through starlight. And when faced with the universe's greatest mysteries, dark matter, the Big Bang, the nature of time, we don't shrug. We build particle colliders deep underground, design space telescopes with mirrors precise to a few atoms, and write equations that stretch the limits of human imagination. The pursuit itself is the triumph, even when answers remain just out of reach. This isn't just about science, it's about storytelling. Every culture, ancient and modern, has creation myths. Now we're writing ours in real time with gravitational waves and quantum fields as our vocabulary. The urge to explore is the urge to belong, to the cosmos, not just to Earth. When a child points a backyard telescope at Saturn's rings or a graduate student crunches data from a distant galaxy, they're participating in the same grand narrative that began when the first humans wondered why the stars moved. So where does this journey lead? Perhaps to Martian colonies or to messages from alien civilizations, maybe to revelations about reality itself that we can't yet fathom. But one thing's certain, the universe won't reveal its secrets to the passive. It takes a species bold enough to ask, stubborn enough to keep searching, and humble enough to marvel at how much remains unknown. And that's what makes us human. Now, as we stand on the brink of the next great revelations, from quantum computers unraveling spacetime's fabric to AI decoding cosmic patterns, remember, exploration isn't just what we do. It's who we are, and the next chapter of this story promises to be the most astonishing yet. The next decade of space exploration promises to rewrite textbooks, with missions poised to peel back cosmic mysteries we've only theorized about. Take the James Webb Space Telescope, fresh off its stunning debut. It's now setting its sights on TRAPPIST-1, a star system with 7 Earth-sized worlds, 3 orbiting in the habitable zone. Webb's infrared eyes will dissect their atmospheres for biosignatures, molecules like methane or oxygen that could hint at life. But here's the kicker: if it finds nothing, that's just as revolutionary. A sterile habitable zone would force us to confront the eerie possibility that life might be rarer than we thought, or that it hides in ways we haven't imagined. Meanwhile, NASA's Artemis program isn't just about returning boots to the moon. It's laying groundwork for humanity's first interplanetary outpost. The Lunar Gateway, a space station orbiting the moon, will serve as a testbed for Mars missions, studying long-term radiation exposure and closed-loop life support. But the real showstopper, Artemis astronauts will explore the moon's south pole, where permanently shadowed craters harbor water ice, a potential resource for fuel and oxygen, turning the moon into a cosmic gas station. Imagine a future where lunar ice fuels ships bound for Jupiter's moons, transforming our solar system into a highway rather than a series of dead ends. Then there's Europa Clipper, slated to launch in 2024. Jupiter's icy moon may hide a subsurface ocean with twice Earth's liquid water, and Clipper will map its thickness, chemistry, and even potential plumes erupting into space. The Daring Pot, NASA considering a tiny submarine to melt through the ice in future missions. A robotic explorer diving into alien darkness, a real-life version of Arthur C. Clarke's vision in 2010, Odyssey 2, but with every leap forward comes ethical quandaries. What if we find microbes on Mars or Europa? Do we have the right to mine asteroids, potentially disrupting celestial bodies older than civilization itself? The Outer Space Treaty of 1967 prohibits national claims on celestial resources, but private companies are already eyeing asteroid metals worth trillions. Will space become a new Wild West, or can we establish frameworks that balance exploration with preservation? And what of the ultimate discovery, a proof of intelligent life? Protocols exist for announcing contact, but no one knows how humanity would truly react. History shows how cultures fracture when worldviews collide. An alien signal could unite us as a species or ignite chaos. The coming missions won't just test our technology, they'll test our wisdom, forcing us to decide whether we're galactic stewards or conquerors. The universe is about to hand us its secrets. The question is, are we ready for what they'll ask of us in return? Every breakthrough in human history has come with a price. Fire warmed us but also burned cities. Nuclear power lights homes but leveled Hiroshima. Now, as we stand on the verge of cracking cosmic mysteries, we face a haunting question. Are some truths better left unknown? Take the search for extraterrestrial intelligence. Finding proof of alien life could unite humanity or shatter worldviews overnight. Religious institutions might reinterpret scriptures. Economies could collapse if alien technology renders our industries obsolete, and militaries would scramble to assess threats from civilizations potentially millions of years ahead of us. The very act of detection carries risk. What if our radio signals attract attention from a species with motives we can't fathom? Scientists like Stephen Hawking warned against broadcasting our location, comparing it to Native Americans encountering Columbus, a meeting where the less advanced culture rarely fares well. Then there's the Pandora's box of space-time manipulation. Theoretical physics teases the possibility of wormholes, warp drives, even time travel. But tinkering with the fabric of reality isn't like engineering a faster rocket. One miscalculation in creating a microscopic black hole could, in the most extreme scenarios, trigger a chain reaction that unravels spacetime itself. The Large Hadron Collider faced lawsuits over such fears, though physicists dismissed them as impossible given Earth's constant bombardment by higher-energy cosmic rays. Still, the ethical dilemma remains. Just because we can probe the universe's deepest levers, does that mean we should? Ancient myths from Icarus to Prometheus warn of hubris, yet curiosity is humanity's oldest compulsion. Discovery doesn't just change what we know, it changes who we are. The Copernican revolution dethroned Earth from the center of the cosmos. Darwin's theories reshaped our understanding of life's origins, and quantum mechanics revealed a universe far stranger than intuition allows. Each upheaval forced society to recalibrate its sense of significance. Now imagine confirming we're not just one planet among many, but one intelligence among countless others. The psychological impact could dwarf all previous paradigm shifts, leaving some feeling liberated and others unmoored. Perhaps the greatest risk isn't finding answers, but losing the questions themselves. Mystery is the womb of wonder. It drives art, philosophy, and science alike. A universe fully explained might become a clockwork toy stripped of awe. The poet Rilke once urged us to love the questions themselves, and there's wisdom in that. Our quest for cosmic understanding isn't just about facts, it's about the act of seeking, the humility to stand beneath the stars and whisper, we don't know yet. That tension between knowledge and mystery may be the very thing that keeps humanity reaching upward, ensuring we never stop growing, never stop dreaming. So look up tonight, not just with the eyes of a scientist or philosopher, but as someone alive in this fleeting moment of cosmic dawn. We're the first generation to glimpse black holes, to touch other worlds with robotic fingers, to decode the quantum whispers of reality. Whatever comes next, whether we choose to listen for alien voices or leave the cosmos its secrets, let it be with open eyes and a reverence for the unknown. Because the universe doesn't just hold truths, it holds the question of what will become when we find them. Take a moment to step outside tonight, not just physically, but mentally, and really look at the sky. Those pinpricks of light aren't just decorations. They're windows into a story where you're both the audience and a character. Think about the Voyager 1 probe's famous pale blue dot photo, where Earth appears as a single pixel suspended in a sunbeam. From that distance, every human who ever lived, every empire that rose and fell, every love story and war and scientific triumph, all of it fits into a speck smaller than a grain of sand. It's humbling, sure, but also electrifying, because that dot, that's us, and the cosmos, it's not just something we observe, it's something we're made of. Let's break that down. Every atom in your body heavier than hydrogen was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, even the gold in your jewelry, all of it was scattered across space by supernova billions of years ago. You're not just in the universe, you're a temporary assembly of its raw materials, a way for the cosmos to look back at itself and ask questions. When you gaze at the Andromeda galaxy, you're not separate from it. You're a conscious fragment of the same process that birthed its swirling arms. This perspective flips the script on feeling small. Yes, we're insignificant in scale, but we're participants in something grand. Consider the James Webb Space Telescope's deep field images, where galaxies swirl like glitter spilled on black velvet. Each of those smudges contains billions of stars, and yet here we are on a rocky planet around an average star, decoding their light. That's not a paradox, it's a revelation. The universe built structures vast enough to defy comprehension, then produced beings capable of comprehending them. So what's your role in all this? You're the universe's way of experiencing itself. Every time you marvel at a sunset, ponder the night sky, or share a discovery with wide-eyed curiosity, you're continuing a chain of awareness that began when the first atoms clumped together. And the wildest part, this story isn't ending. It's accelerating, with telescopes peering back to the cosmic dawn, probes touching alien worlds, and experiments unraveling quantum secrets. We're not passive observers. We're the universe waking up, stretching its limbs, and reaching for the next chapter. As we wrap up, hold onto this thought: the cosmos didn't just happen to you. In a very real sense, it happened for you, for the chance to be here now, eyes wide open to the wonder. Whether you're a scientist, a stargazer, or someone who just paused to look up on a clear night, you're part of the universe's greatest trick, turning stardust into sentience and emptiness into awe. And that's a story worth telling. From the invisible grip of dark matter holding galaxies together to the phantom push of dark energy tearing them apart, we've explored mysteries that defy intuition. We've stood at the edge of black holes where time slows to a crawl, and peered into the quantum realm where particles whisper to each other across light years. We've imagined wormholes stitching the cosmos together and parallel universes branching with every decision. Each revelation peels back another layer, revealing a universe far stranger, more interconnected, and more alive with possibility than we ever imagined. Think about dark matter, an unseen architect shaping the cosmos. its presence felt only by the way stars whirl too fast at galaxy edges, or dark energy, that mysterious force accelerating the universe's expansion, as if space itself has a hidden heartbeat. These aren't just gaps in our knowledge, they're clues that reality operates on rules we're only beginning to decode. Even time, that steady march we take for granted, bends and warps, suggesting that past, present, and future might all exist at once in a frozen cosmic block. Then there's the quantum realm, where particles exist in multiple states until observed, as if reality itself waits for an audience. Entanglement ties distant particles together in instant harmony, hinting at a universe where separation is an illusion. And lurking in the equations are wormholes, shortcuts through spacetime that could link distant stars or even different eras, if only we could find them. But the biggest twist, this might all be one version of the story. The multiverse theory suggests countless alternate realities, each with different laws, different histories, even different versions of you. Somewhere, a universe might exist where gravity is stronger, where life never arose, or where you made that left turn instead of right. It's a dizzying thought, but it underscores the most humbling truth. The universe doesn't just exceed our understanding, it constantly redefines it. So what's next? The greatest adventure lies in the questions we haven't even thought to ask yet. That's where you come in. Whether you're a seasoned stargazer or someone who just paused to look up tonight, you're part of this story. Share your wonder, chase your curiosity, and never stop asking why. Because the universe isn't just something we study, it's something we experience, one awe-struck moment at a time. And the next chapter, it's yours to write. The universe doesn't owe us answers, it offers mysteries, and that's the gift. Every discovery we've made, from the cosmic microwave background to the quantum entanglement of particles, hasn't closed the book on reality. It's torn out the page and handed us a blank one. Think about that for a moment. The same cosmos that carved galaxies from the chaos of the Big Bang is still unfolding, still evolving, and somehow, against all odds, it gave rise to creatures who can not only witness its grandeur but question it. That's the real magic. You, staring up at the stars tonight, are part of an unbroken chain of curiosity, stretching back to the first humans who traced constellations in firelight. And the chain doesn't end here. Consider the Voyager probes now drifting beyond our solar system, carrying golden records etched with the sounds of Earth, a child's laughter, a thunderstorm, the crackle of fire. They're time capsules, yes, but also declarations. We were here, we wondered. Decades from now, long after those probes fall silent, their journey will continue, a testament to humanity's refusal to be bound by horizons. That's the spirit we carry forward. Whether it's a teenager pointing a telescope at Jupiter or a team of scientists decoding the whispers of gravitational waves, every act of exploration is a rebellion against indifference. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That's the heart of it. The universe isn't a puzzle to be solved. It's a conversation, one where every generation gets to add a sentence. Maybe you'll be the one to crack dark matter's code, or your child will spot the first flicker of alien life. Or perhaps your role is simpler, to look up and feel that ache of wonder to keep the questions alive. Because the day we stop asking is the day the cosmos becomes background noise. So here's your invitation. Share your thoughts in the comments. What cosmic mystery keeps you up at night? Hit subscribe to join us as we chase the next revelation, from the oceans of Europa to the holographic edges of reality. And tonight, when you step outside, remember, you're not just a spectator. You're the universe, awake and aching to know itself. The story's still being written. Turn